You've already learned how to figure out if an individual bond is polar or not. In other words, are the electrons going to shift down to one end of that bond, or are they going to kind of be equally shared between the two atoms? You've already learned that part, and right now what we want to do is look at an entire molecule. With the molecule as a whole, will we get an electron shift towards one direction, or with the molecule as a whole, is there kind of equal electron density all the way around? And that's going to really affect their properties, and we'll talk about that a little bit later. But let's look at these different shapes that you're already familiar with. So let's say that we have something that's linear like this. Now, first of all, the rule is that if the bonds are not polar, the molecule cannot possibly be polar. If we've got equal sharing with all the bonds, then there's going to be equal sharing for the molecule as a whole, and hopefully that makes sense to you. So what I'm going to talk about in these examples is just the cases where the bonds themselves are polar, but we want to say, is the molecule as a whole polar? Because sometimes it isn't. So consider a couple of different options. With our linear arrangement here, we might have something like this, where we've got this polar bond and this polar bond, and you can see that the electron shift overall is going in that direction. So in that case, yes, we would have a polar molecule there. Now, what would happen though if we turn this around and now we have a bond that's like that? So now we have electrons being pulled in two opposite directions, and those cancel each other out. So as a whole, this molecule is not polar. Now if it is polar, we call it a dipole. D-I-P-O-L-E. So we would say this molecule is a dipole if overall it is polar. And we would just say it's not a dipole, or it's a nonpolar molecule if overall it's not polar. All right, let's go back to another shape. Now, this is the kind of thing where we might have polarity that looks like that. So we've got electrons being pulled in this direction and electrons being pulled in that direction. So what we do with this kind of molecule is say, overall, we do have a shift that's in general toward the bottom of that molecule. And so we would say, yes, that is a dipole. Now, another thing that can happen with these is maybe they're like that. This happens with water, by the way. So overall, we have a shift that goes to the top of the molecule, and we would say, yes, that is a dipole. Now, what if we did this, though? What if we did... So maybe these three are all different, and maybe we've got polarity like this and polarity like that. In that case, we have some being drawn to the top of the molecule and some being drawn to the bottom of the molecule, and we say no, those are going to cancel each other out. That is not going to be a polar molecule. So looking at this is our pyramid. Most often you're going to have examples where these three atoms are all the same. So maybe you'll have polarity going in this direction. We would consider that the bottom of the molecule. Think of the pyramid standing on ground, or that three-legged stool we talked about before standing on the ground. So we have the top of the stool and the bottom of the stool. So if electrons are being drawn to the top, or if they're being drawn to the bottom, either way we're going to call that a polar molecule. Now, if we did have a situation where these were not all the same, and maybe some are going this way and some are going that way, then probably overall that's not going to be very polar. But I wouldn't give you something like that this year because that's a little too much. So in these cases, we'll have all atoms the same, and if the bonds are polar, then that's going to end up being a polar molecule. So it might be pulled this way, and in that case you draw a big arrow going like that. If the bonds went the other way, and if the central atom was the most electronegative, so let's draw a picture of that. Let's say we have this, and let's say that all the bonds are polar in this direction. That's kind of like everything being pulled to the top of the molecule, and you would draw a big arrow like that, and you'd say, yes, that is a dipole. All right, you are much less likely to get polar molecules with these arrangements because even if the bonds are polar, let's say, now that statement assumes that the outside atoms are the same. If you have some mixture of outside atoms, then you can very easily get polarity. So let's think about that. Let's think about if all of these bonds are polar and all of the electrons are being pulled toward the outside atoms. Those are going to cancel each other out, not a polar molecule. Same thing's going to go on here. If all the electrons are being pulled outward, those are going to cancel each other out, not a polar molecule. If they're all being pulled inward, if these are all polar in the direction of the central atom, again, not polar. If these are all being pulled inward, not polar. But you might see a situation where, let's say these are polar like this, and this one goes like that. So we have something of very high electronegativity up there. Maybe that's fluorine. And maybe this is carbon, and maybe these three are hydrogens. And so you have your lowest electronegativities in these three, and a medium and a higher. And now maybe you can see that that's all going to be shifted kind of in the upward direction. And I would draw an arrow like that and say, yes, that could be a polar molecule. So you can kind of see that the shape affects this a whole lot. You could get that same kind of thing going on here too. Like you could have that and this and this. And that overall would kind of give you a big upward range like that. Here's a good example of that. Hydrogen, carbon, hydrogen, double bond, oxygen. These are the lowest, and this is medium, and that's highest. So overall, you have a polar molecule like that. So I hope that helps. You'll have lots of examples to try for yourself and kind of play around with it and work these things out.